Well, thank you all so much for being here for my dissertation defense. I've been working on a PhD for about the past 4 years now, and I'm really excited to be able to talk about my research and the things that I've been working on for the past 4 years. So, before I move on to some of the specifics of my research, let me talk a little bit about wind energy in general. So, wind energy really is amazing. It produces no harmful emissions during energy production. In addition, it requires very little water during energy production and has no chance of polluting groundwater supplies. On top of that, wind energy requires no fuel. And finally, wind energy is cheap. Now, in past decades, this certainly was not the case. In fact, wind energy was notorious for being very expensive and not at all economically viable without large government subsidies. However, since then, entire research careers and millions of dollars have been spent in order to improve wind energy technology and reduce the cost of producing electricity from wind, such that today, wind is one of the cheapest, and in many areas is the um, um, cheapest forms of energy. So because of all these great benefits, and in a large part due to the economic drivers, wind energy produces a large share of electricity in the United States and throughout the world. Last year, wind produced more than 7% of the electricity in the United States, and this number is projected to continue to grow in coming years. So as more and more wind turbines are built throughout the world, they will be built in wind farms or groups of wind turbines that are built relatively close together. So this produces a lot of logistical benefits, building turbines close together. However, it also causes there are also some downsides to building turbines close together. And one of the main downsides is wake interference between turbines. So when wind passes by a turbine, some of the kinetic energy is removed and converted to electricity, which we use. However, because some of the energy is removed, the wind behind a turbine is moving slowly. And this area of slow moving air is known as a wake and is detrimental in a wind farm because it reduces the amount of energy available for the rest of the turbines to extract. So one way to avoid the downsides of wake interactions between turbines is through wind farm layout optimization. So in theory, this is a really simple idea. It means build turbines in the locations where they will not be affected by the wakes of upstream turbines. So if you'll look at this example that I have shown here, if you have a very simple 4-turbine wind farm, assuming the wind is coming from left to right, you can see that the upstream wind turbines are exposed to the free stream air, the free stream wind, and will therefore be able to produce a lot of energy. However, the downstream wind turbines are waked, meaning the wind coming into contact with these turbines is moving much slower, so they will not be able to produce as much energy. However, if we rearrange the locations of the turbines, as shown here on the right, you can create a wind farm layout where every wind turbine is able to experience the free stream wind and able to produce a lot of energy. So in theory, this is a really simple and straightforward idea. However, in practice, it gets to be a lot more complicated because wind does not always come from the same direction. In fact, wind can come from any direction with a certain probability. So in the wind industry, wind probability distributions, wind direction probability distributions are usually represented as a windrows, as shown here on the right, where the length of each one of these bars represents the probability of wind coming from the indicated direction. So if we go back to the simple example that I showed before, if I told you the wind is always coming from left to right, I feel pretty confident that anyone here could use their intuition and say, I can rearrange these turbines to find a good layout that will produce a lot of energy. However, if I changed the rules now and I said, well, now the wind can come from any direction with the probability indicated by this wind rose, I think it'd be a lot harder for most of us to use our intuition and find a layout that optimizes the energy production of this wind farm. So this is a really complex problem because these are 4 wind turbine farms, and what we care about are wind farms that are much larger, that have maybe hundreds of wind turbines. So the interactions between the wind turbines are very complex, and it's hard to use intuition to find the best layout. So what I've used in my research is gradient-based optimization to solve the wind farm layout optimization problem and improve its application. So gradient-based optimization is an advanced optimization technique that utilizes information about function gradients in order to find a solution. So it requires more work on the user's part, so on my side, because it means that I needed to calculate my model gradients in addition to the model outputs in order to provide that to the optimization algorithm. And this is no trivial task. So obtaining function gradients has taken months of researchers' time, and for me has taken months to be able to obtain function gradients and apply them in optimization studies. So why would I use gradient-based optimization if a simpler method is out there? Well, with gradient-based optimization using exact analytic gradients, I can optimize very large problems with a lot of design variables. In general, optimization problems take a long time, the computational expense required to optimize a certain function scales very poorly with the number of design variables that are used. And the scaling is different depending on the optimization method that is used. So if you look at this figure here, if I'm using a gradient-free method, shown with these red dots, the computational expense shown with a rough estimate of time here on the y-axis scales very poorly as I increase the number of design variables. However, if I'm using gradient-based optimization with exact analytic gradients, the computational expense does increase with increasing design variables, however, much more favorably, allowing the user to optimize large problems in a computationally efficient method. So with that said, with that introduction, let me move on to some of the specifics of my research. As I said before, my research has been involved in improving wind farm optimization. And within this area, I've done, I've looked into a few specific topics. So first, I'll talk about coupled wind turbine design and wind farm layout optimization. After that, I'll introduce a parameterization method that I developed to define the location of wind turbines in a farm with very few design variables. And finally, I'll introduce a model that I developed to calculate the fatigue damage of turbines in a wind farm in a computationally efficient way. So first, I'll talk about coupled turbine design and wind farm layout optimization. I already explained how wind farms can be improved by optimizing the layout to avoid wake interference between wind turbines. And that's a large driver. Oh, my light's turned off. That's a large driver in the performance of a wind farm. However, another important driver in wind farm performance is the turbine design itself. This is usually done, the design of a wind turbine and then the layout optimization of the wind farm is usually done in a sequential manner, meaning that the turbine is fully designed and optimized for the expected conditions in which it will operate. And then that turbine design is used in a wind farm layout optimization. So in my research for this study, Dr. Ning and I said, well, rather than doing this sequentially, of doing turbine design, then layout optimization. Let's do them both at the same time, of turbine design and layout optimization, so that the turbines can be optimized exactly for the conditions in which they will operate, which include wakes. This also introduces some really cool possibilities of being able to use different turbine designs throughout your wind farm. Rather than assuming that all the turbines are exactly the same, you can allow turbines to be optimized individually for the exact circumstances, conditions in which they will operate. So this is not a completely new idea. It has been approached in the past. There have been several studies that have looked at optimizing the heights of wind turbines in a wind farm, or allowing different heights of turbines. And I've also encountered a lot of studies that have used some pre-selected turbine designs and then used optimization to find the best combination of these pre-designed turbines to use in a wind farm. And these studies have done an excellent job and laid some really great groundwork for what I've done. However, they have neglected a few important things that I've considered in my studies. So first, past studies in this area have used few design variables. They've either only considered a small part of turbine design, or they've pre-designed the wind turbine and selected from a few pre-designed turbines, as I've explained. Second, past studies have ignored costs. So as you change turbine design, you can't decouple that from the additional costs that are required to build and maintain the turbines. And third, all studies that I've encountered in this area in the past have ignored the structure. As you build taller turbines and have larger rotors, the loads experienced by the turbine will be larger and the loads experienced by the structure will be larger, and you need to take that into account when designing the wind turbine. So the goal of my study was to approach full wind turbine design and couple that with the wind farm layout optimization. So by full wind turbine design, I mean the following design variables: turbine height, rotor diameter, and turbine power rating. In addition, I optimized the chord and twist distribution along the blade. And finally, I optimized the wind farm tower diameter and thickness at various stations along the height of the tower. So this study was so interesting and so cool because I was able to combine several different scales of models and several different disciplines into one global model, so I could couple the turbine design and the wind farm layout optimization. So by different scales, I mean different physical scales. I'm optimizing things as small as the tower thickness, which is on the scale of millimeters, all the way through the turbine layouts, which is in scales of meters or kilometers. In addition, we're using combining different disciplines of models, including the structural models to evaluate the wind turbine, the cost models to evaluate the cost of the different turbine designs, and finally, we're using fluid models to take into account the wake effects between turbines in the wind farm. And this is really interesting. On top of that, I obtained gradients for all of these models, allowing us to optimize huge numbers of design variables. So by coupling together all of these models, I was able to perform gradient-based optimization of the wind farm layout and the turbine design. So this is a little animation that I created to demonstrate the progression of the design variables throughout the optimization. So here on the top left, you can see the wind farm layout, where each of the dots represents the location of a wind turbine and how it changes throughout the optimization. Here on the top right, you can see the wind turbine design variables. This indicates the rotor diameter and the turbine hub heights. You'll see that in this optimization, I have only two turbine designs allowed throughout the farm. I've forced all of the wind turbines to be one of two turbine designs, and I'll talk a little bit more about that coming up. And finally, here on the right is the wind farm performance, or the cost of energy of the wind farm as it progresses through the optimization. And you'll see that the cost of energy decreases as we reach a more optimal point. So by combining all of these models, I was able to perform coupled wind turbine design and layout optimization. So the question now that I wanted to explore was what scenarios would benefit most from performing this coupled optimization, and what scenarios would benefit most from allowing different turbine designs in the same wind farm. So I explored how do these optimization methods perform for different sizes of wind farms. So in each of these wind farms, there are the same number of wind turbines. However, the area in which they are, the geographical area is larger in some, meaning that the spacing between the turbines is different for each of these different wind farms. So here are some of the results of this, this research. On the y-axis here is the cost of energy of the optimized wind farms of each scenario. And on the x-axis, you can see the small, medium, and large wind farms. The gray dots represent a sequential optimization in which I performed the wind farm design, the wind turbine design, followed by the wind farm layout optimization. The gray squares represent the coupled optimization, where I performed the wind turbine design and the wind farm layout optimization at the same time. However, with the black squares, it's with the assumption that all of the wind turbines throughout the farm are exactly the same. So you'll see that for this small wind farm, there is a huge benefit to performing coupled turbine design and layout optimization. And for the medium wind farm, there is still a benefit, however, it is not as pronounced. And for the large wind farm, performing coupled optimization is not significantly beneficial over doing the optimization sequentially. Now, here I'm adding on some data points in which I allowed there to be two different turbine design groups throughout the wind farm. You'll notice here that compared to the black squares, which represent one turbine design group, when I allow two turbine design groups throughout the farm, it performs significantly better in the small wind farm. That's about a 10% improvement reduction in the cost of energy when I allow two different turbine designs throughout the farm. However, for the medium and the large wind farms, there's not a significant benefit to allowing two different turbine designs in the same farm. So why is that? For a small wind farm, the turbines are spaced very close together, which means that the wake deficits are very large. So in these small wind farms, I can use layout optimization to move my turbines around and avoid wakes. However, if I allow different turbine designs, I can also change the heights of the wind turbines to allow further avoidance of the wakes, which is important and allows us to greatly reduce the cost of energy. However, for the larger, medium and large wind farms, there's not a significant benefit to allowing two different heights or two different turbine designs, because there is enough freedom to avoid the wakes in the two-dimensional plane. So I spoke about how with two different turbine design groups, we're able to achieve a significant benefit, a significant improvement in our wind farm performance. So the logical progression would be, well, if I can obtain significant benefit from using two different turbine design groups, what if I used more? What if I included more turbine design groups, or even allowed every wind turbine in the farm to be optimized individually? So we thought of that, and I performed a study to see how does increasing the number of turbine design groups further improve the performance of the wind farm. So here on the top left point, this is an optimized wind farm with one turbine design group. And here is the performance of a wind farm with two different groups. And you'll see significant improvement from two groups to one group. However, as we further increase the number of turbine design groups in the wind farm, all the way up to optimizing the design of every single turbine individually, you do not obtain further benefit beyond just using two different design groups. So that's important and really, really useful, because it means that we can obtain the majority of the benefit of using two different turbine designs in your wind farm for the minimal number of design variables required. Because now, rather than needing to optimize every turbine individually, we just need to optimize the design of two different wind turbines in the farm. So what is the impact of this specific study that I've spoken about? So first, I developed a methodology that combines several different scales of models and several different disciplines, as well as obtaining exact analytic gradients, which allow coupled optimization of the full wind turbine design and the wind farm layout. This is something that had not been done before and is important to further improve wind farm performance. The other large impact of this is the recognition that we can achieve the majority of the benefit of having different turbine designs throughout a farm with only two different turbine design groups. So let's move on. The next topic which I'm going to speak about is a parameterization method that I developed to greatly reduce the number of variables required in wind farm layout optimization. So in the past, wind farm layouts were usually defined in one of two ways. So one, they're defined as a grid. This is very simple. It requires very few design variables, maybe a X and Y spacing of the grid, a grid shear variable to define offset between rows, and perhaps a rotation variable of the grid. This is great. It requires very few design variables and it's very simple. However, it often leads to simplistic layouts that underperform. Now, the other commonly used method is to define the layout of every wind turbine directly, individually. So this allows the most freedom. However, it also requires the most design variables. So for very small wind farms with relatively few wind turbines, this is all well and good. However, as we increase to larger wind farms, it requires more and more design variables, which, if you remember before, the computational expense of optimization scales poorly with increasing design variables. So I've performed many optimizations, many wind farm optimizations throughout my graduate studies. And what I realized was the optimal wind farm layouts often followed a very similar pattern. So this is an optimized layout shown here on the right. And let me point out a couple things about this wind farm layout. First is that many of the turbines are placed around the wind farm boundary. They're exactly on the wind farm boundary. This makes sense because you want to best utilize the space that you're given for an optimal layout. Second, the wind turbines within the wind farm are loosely spaced in these rows. You can see row patterns throughout the wind, the rest of the turbines in the wind farm. Now that doesn't exactly apply to every single turbine. There are a few stragglers here, but in general, you can see that pattern within the wind farm layout. And these patterns were the same for many other optimizations that I ran. So I created a parameterization method that forces these observations upon the wind farm layout. First, about half of the wind turbines are placed around the wind farm boundary, equally spaced around the perimeter. So all of these wind turbines are defined with one design variable, which allows the turbines to slide around the wind farm perimeter while maintaining their equal spacing. The rest of the turbines are shown here in these rows in the middle of the wind farm, or in this wide space grid in the middle of the farm. So the rest of these wind turbines are defined with four design variables: an X spacing, a Y spacing, a grid shear, and a rotation variable, which define the inner grid. So you'll see there's the boundary turbines and the grid in the center. So I've called this the boundary grid parameterization method. So great. I can define that layout as I've defined if I want to. That's anyone can do that. However, how does this actually perform? What utility does this give us? So in order to determine if this was actually useful, I ran tens of thousands of individual optimizations in order to determine, well, what does this work? Does this work in most scenarios? Does this work in all scenarios? And here's what I found. So with each layout definition method, the grid, the boundary grid, and the direct method, I optimized I ran 100 optimizations with randomly initialized design variables for many different scenarios. For different turbine spacings, as shown here on the left, for different wind roses, shown here in the middle, and for different wind farm boundaries, as shown here on the right. And in these figures, I'm showing the best wind farm layout that I achieved with the 100 optimizations. So if we'll first look at the grid layout definition method, represented here in yellow. For each of the cases, the yellow points perform better than the baseline. However, they do not perform as well as the other methods. Now, the blue points, which represent my boundary grid parameterization, and the red points represent the direct method, where the location of every turbine is defined individually. So you'll see that the blue points, that my method, performs just as well and even slightly better than the wind farms that were optimized directly. So this is really cool because it only requires 5 variables. With 5 optimized variables, I'm able to obtain wind farm layouts that perform just as well as wind farms that have been optimized directly. So let's look at another metric that we care about. We care about how the final wind farm performs, but we also care about how hard it is to reach that solution. What is the computational expense of running this optimization? So these are histograms of each of the 100 optimizations that were run for the different boundary shapes and for each of the layout definition methods. So you'll see for this complex boundary here on the left, and for the square boundary here on the right, my boundary grid parameterization, represented with the blue histogram, requires about an order of magnitude fewer function calls to reach an optimized solution compared to the direct optimization. For the simple circle shown here in the middle, the number of function calls was about the same, which is surprising, and kudos to the direct method for that. So let's look at this again, remembering that what I've done in this study is used exact analytic gradients with gradient-based optimization, which usually scales very well with increasing design variables. Now, with the direct method, which requires about 200 design variables for this method, wind farms that I've optimized, you'll see that with 200 design variables and exact analytic gradients, we were able to perform the optimization relatively quickly. However, because there are so many design variables, had we been using finite difference gradients or a gradient-free optimization method, it would have taken much, much longer to find a solution, and so long, in fact, that it would have been prohibitively expensive. However, using my boundary grid parameterization method, which required only 5 design variables, even if we were to use a different gradient, a different optimization method, such as finite difference gradients or a gradient-free method, we would be able to reach a solution in a time frame that is feasible for what we're interested in. On top of that, we're able to reach solutions that perform just as well as the direct method. So what is the impact of this study? First, I developed a wind farm layout definition that is able to define the layout of any wind farm with any number of wind turbines with only 5 design variables. And on top of that, when these design variables are optimized, I'm able to create wind farm layouts that perform just as well as wind farm layouts that have been optimized with each of the wind turbines defined individually. Second, because there are so few design variables required, it allows users to use gradient-free methods and finite difference gradients in order to optimize the layout of large wind farms. So I'm not aware of very many organizations that use gradient-based optimization. The majority of the wind industry uses gradient-free optimization techniques and is therefore limited in the size of the wind farms that they can explore and optimize well because of the computational expense. However, with this parameterization method, it opens the door for the exploration of much larger wind farms. Let me grab some water before I continue. So the final topic that I'll discuss is a model that I created to calculate fatigue of wind turbines caused by partial waking. I already spoke about how wakes are detrimental in a wind farm because they reduce the amount of energy available to the rest of the wind farm. However, in addition to reducing the amount of energy available, wakes are detrimental because they can increase fatigue damage on turbines. Fatigue damage is caused by cyclic loading for a long period of time, which is exactly the situation that wind turbines operate in. They're cyclic by nature, wind turbines spin, and they're expected to operate for many years, 20 to 25 years with minimal maintenance and downtime. So when operating in a partial waking condition, this can exacerbate the already present cyclic loading. So if a turbine is partially waked, meaning it's waked on one side of the rotation and not on the other, it means that it experiences fast wind speeds on one side and slow wind speeds on the other, which compound the cyclic loading that the turbine already experiences. So everyone already knows about this. This is something that everyone's aware of. However, in the past, people have not included wind turbine fatigue constraints or considerations within a layout optimization because fatigue models have been prohibitively computationally expensive. The fatigue model that I'm most familiar with takes about 20 to 30 seconds, up to several minutes, in order to analyze a single wind turbine. So now if you need to analyze an entire wind farm, plus do this in an optimization framework, it would be impossible to include the fatigue using this model in a wind farm layout optimization study. So I created a model that is able to compute wind turbine fatigue in a computationally efficient way, which can be used in a layout optimization study. So let me explain briefly what I did with this model in order to be able to compute the fatigue on a wind turbine. So first, let me use my mouse here to show, excuse me. So first I computed the wind speeds across the wind turbine blade at 2 different azimuth angles. I did that at 90 degrees and 270 degrees as shown here in this figure, which corresponds to the angles where the blade is parallel to the ground. At these angles, the blade experiences its largest gravitational moments, as well as the largest differences in the wind speeds that are caused by partial waking. So with these wind speeds that I calculated with an analytic wake model, I was able to use steady state models to calculate the loads experienced by the wind turbine along the blade. And from these loads, calculate root bending moments and stresses experienced by the structure, experienced by the blade in these steady state conditions. So this gave me a steady state stress history. However, and this is important for the fatigue. However, in addition to the steady state history, it is also important to consider the turbulence in the wind, which also greatly contributes to the fatigue damage experienced by a wind turbine. Oh, excuse me. So in order to account for the turbulence in the wind, I created a turbulence distribution. A representative example is shown here on the top right. And then I scaled the wind speeds that I calculated in the steady state wind speeds. I scaled those wind speeds with the turbulence distribution and the ambient turbulence, and I used a model to predict the additional turbulence caused by the turbine wake. With these new turbulent wind speeds, I then scaled the steady state stresses that I calculated in the last step to create a turbulent stress history. So moving on, after obtaining this turbulent stress history, I used pretty typical methods that are used to calculate fatigue damage on the structure. First, I used rainfall counting to extract the alternating loads contained within this noisy stress history. I used Goodman correction to account for the mean loading, the mean loading value. I also, I then used I then calculated the cycles to failure for each load cycle and used Miner's rule to calculate the total damage that a wind turbine experienced at a given loading condition. So now the question is, well, how does my model perform? I'm showing here my model represented with the orange line compared to some very high fidelity models, which are a LES run coupled with a dynamic aerostructural model to calculate the fatigue damage. So I'm comparing damage calculated by my model to this very high fidelity model. And the x-axis is a sweep across a turbine wake. So if you look here on the left, we have an upstream wind turbine shown here, and I'm going to sweep a downstream wind turbine across the wake and calculate the damage for different amounts of partial waking. So this is a matrix showing how my model performs compared to the high fidelity data for several different scenarios. So each row represents a different free stream wind speed, and each column represents a different distance downstream that I'm calculating this damage. So you'll immediately notice that my model exactly predicts the trends of location of worst damage. And this is really important because it allows us in optimization to be able to avoid these locations that are extremely detrimental to the structure. So in addition to the location of maximum damage, we're also very well predicting the relative difference between the distances downstream and the different wind speeds, the same relative differences that are shown with the higher fidelity model. So you'll notice, I'm assuming some people are looking at this and saying, well, look at the orange model. It doesn't exactly match up with the blue dots. This model can't be that good. And I'll remind you that in fatigue calculations, there are very large exponents involved. And in this case, there was a 10th power involved in the calculations. which means that any small variations in the actual stress history and my predicted stress history are compounded by a factor of 10. So being able to predict the trends and the relative values are the most important part of this model. And being able to even closely approximate the final damage value is pretty impressive. I'm very satisfied with that. So you'll notice here that for different amounts of partial waking, for one side, when the turbine is partially waked on one side, the damage is greatly increased. However, if the turbine is partially waked on the other side, there's not the same huge increase in damage, which is initially non-intuitive, or at least it was for me. You would expect that if the turbine is partially waked on either side, you would get some increase in the damage of the wind turbine. However, there's a relatively simple explanation for this phenomenon. So first, if we look at a turbine in free stream wind conditions, there's no waking and the aerodynamic loads are the same for the turbine throughout its rotation. On one side, the aerodynamic loads and the gravitational loads are in different directions. On the other side of the rotation, the aerodynamic loads and the gravitational loads are in the same direction. So if we take off these blades and put them side by side, so it's a little bit easier to visualize, and then here on the far right, I'm combining the aerodynamic and the gravitational loads for a resultant load value. Now, if the turbine is partially waked on one side, on side one shown here, the wind is moving slower, which means that the aerodynamic loads are smaller. Therefore, the loads which are resisting the gravity are smaller. This means that the combined loads shown here on the far right for side one are now a larger magnitude in the opposite direction. And if you'll see, the difference between the loads in the free stream case is smaller than the difference between the loads in the partially waked case. That means if the turbine is partially waked on this side, it experiences more damage, and this is detrimental to the structure. However, if the turbine is partially waked on the other side, on the side where the aerodynamic loads and the gravitational loads are pointing in the same direction, it actually reduces the difference between the load values on different sides of the wind turbine. And this is why it's detrimental to be partially waked on one side, but not detrimental to be partially waked on the other side. So I applied my fatigue model to a wind farm layout optimization in order to constrain the damage value experienced by all of the turbines in the wind farm. So I started by simply performing a wind farm layout optimization without considering the fatigue. So you'll see here, this is the wind farm layout obtained by optimizing the layout of a wind farm. And down here at the bottom, you'll see the damage of all of the wind turbines in the wind farm. You'll see that there's a pretty big spread in the damage experienced, and you'll see one outlier that has a very large damage, and this is very undesirable. Now, using my model, I used this layout on the left as a starting point and ran another optimization in which I constrained the fatigue damage of all of the turbines to be below 0.2, which you'll see here on the bottom. You'll see that it was successful, and I was able to successfully constrain the damage of all of the turbines in the wind farm to be below my desired value of 0.2. So let me point out a couple things in this slide. First, why did I choose 0.2 as my damage constraint value? In fatigue damage, damage value of 1 indicates failure. So choosing, it may seem logical to choose a value of 1 as my constraint. However, for wind turbines, extreme events often contribute to fatigue damage, such as large gusts or extreme wind speeds experienced throughout the life of a wind turbine. Therefore, these are not, I'm not capturing these events in my model. I'm only considering the damage accumulated by a wind turbine during partial waking. So therefore I need to choose some value less than 1, and for this optimization I chose 0.2. Another thing to see is that here on the top right, the wind farm layout is not hugely different than that one shown on the left. So that's because I used this layout here on the left as a starting point for the optimization on the right. And you'll notice the biggest difference is here or around the right boundary, where the turbines are very close together. So when the turbines are close together, the fatigue damage from partial waking was the worst, because this means that if a turbine is partially waked, there's a large speed difference on different sides of the rotation. Therefore, in these locations, it was very important to move turbines to locations where they would not experience significant amounts of partial waking. So what is the impact of this model, of this study? I was able to create a fatigue model which sufficiently accurately and quickly calculates fatigue damage on wind turbines. This is important because it means that it can be used in a wind farm layout optimization in order to constrain damage caused by partial waking in a wind farm. So to quickly review, I've spoken about several studies I performed in order to improve wind farm optimization and design. First was coupled to wind turbine and wind farm layout optimization. Second was a parameterization definition that I created in order to greatly reduce the number of variables required in wind farm layout optimization. And finally was a model that I created to calculate wind turbine fatigue, which can be used in an optimization framework. And what are the fundamental contributions to knowledge of each of these studies? So I've already mentioned these, but I'll go over them again to really reiterate what my contributions are. First, I created a model and a methodology to perform coupled optimization of wind turbine design and wind farm layout. This combines several different scales of models and several different disciplines, as well as me obtaining exact analytic gradients for these models in order to optimize many design variables and understand the conditions in which coupled optimization and wind farms with different turbine designs throughout the farm are most desirable. Second, I created a wind farm layout parameterization, which defines the layout of any wind farm with only 5 design variables. And this is independent of the number of turbines on the farm. Now, on top of that, the layouts optimized by my parameterization method perform just as well and even slightly better than wind farms that were optimized with the location of every turbine defined individually. This is extremely important for people who use gradient-free optimization and for people who wish to optimize large wind farms. And finally, I created a model which accurately predicts wind turbine fatigue and is computationally efficient enough to be used in a wind farm layout optimization study. So as a graduate student, I've been extremely lucky to be part of the Flow Lab at BYU. We've had high expectations and given a lot of opportunities to publish and take part in academic work. So as a PhD student, I've been able to author 6 journal publications, and 4 of those as the first author. Additionally, I've been able to author 5 conference publications, and 3 of those as the first author. As well as my publication record, I've been able to present at 4 conferences to a technical and an academic audience, and I've loved being able to do that. Additionally, I've been able to mentor students, help with research proposals, and be a peer review for the journal publications of others in the wind field. So I know I haven't solved every single problem in the wind industry. However, I hope and I expect that my research as a graduate student will be able to immediately be applied and impact the wind industry. So thank you.